So let's start. Hello again. My name is Alhaad Gokhale. I'm a tech lead manager on Google Search, and my team focuses on live updating data within search. So, for example, if you search for cricket, you'll see like the first result as a one box which has live updating data, and that is what I work on. So live updating data is not just for sports, but also election results, which where live updating data comes in. There is weather, there's finance, and lots of users within Google, and that's what my team focuses and specializes on. So here are like some interesting things that the team has worked on. So cricket, I guess you might be following the sensational and fascinating game that finished today. Uh, so this is what I work on. And here I've given three examples. First one is cricket. Second one is US election results. And third one, I've gone in a more complicated query that kind of takes us closer to the topic of natural language processing. How many centuries does Virat Kohli have in ODIs? If you search this on Google today, you'll get a direct answer. We are able to like identify what the user is asking and fulfill the request, right? And this is where my day-to-day work with NLP comes in. And beyond how many centuries does Virat Kohli have in ODIs, users can ask who won the World Cup, right? And it can be not just for cricket, other sports like how many three-pointers does LeBron James have, and the queries can start getting arbitrarily complex. Like you can ask how many points did LeBron James have in the 2018 season when playing against a particular team, right? And you can imagine this query getting even more complex. Uh, Today if you search in Google, we are able to answer all these queries, but yes, this is an area that is still under active development, a lot of active investment, and we expect the state of the art to improve significantly over the coming years, right? And for this session, as I said, my goal is to convey some challenges that we face in the domain, and I will phrase those challenges as a practitioner of NLP, right? Highlight some insights, some learnings that we have had while solving these problems in the real world, and give you a glimpse of how a Google scale system is created by taking a case study of an example of conversational search, and we'll take up an example of shopping. And obviously, like with everything in the real world, there is no secret sauce. There's no magic bullets. It's a lot of hard work. Cool. So let me ask you this: like, can folks tell me who this is? This is a very famous computer scientist. Maybe you can reply in chat or speak
Yes.
out.
Yes, Sudhanshu.
Alan Turing.
That is correct. This is indeed the picture of Alan Turing, and Alan Turing is considered the founder of computer science. The Nobel Prize in Computer Science is called the Turing Award and is named after Alan Turing. And so Alan Turing, in his the foundational paper, it's called Turing Test. It's a part of the Church Turing thesis. Starts his paper by saying, "I propose to consider the question: Can machines think?" That's how he starts. Can machines really think? And this was, I think, sometime in the 1940s or 50s. So well before present artificial intelligence, well before even the microprocessors we have today. And in this case, that Alan Turing's genius was to kind of in unambiguous and concrete words define a test that says whether a system is intelligent or not. So he says, I propose to replace the question by another. So instead of saying, can machines think, right? He replaces it with an unambiguous statement, which is this. I'll try to paraphrase what's happening. So in this world, there are three actors, A, B, and C, right? C, A, B, A is a so C aims to distinguish. So A A and B are separated from C by a barrier. It might be a physical barrier. It might be a network barrier. Like they might be speaking on Zoom. I don't know, right? And C aims to distinguish between A and B, that who out of A is a man and who out of B is a woman, right? And A's aim is to fool C into an incorrect decision, but B's aim is to help C arrive at the right decision, right? So this is the setup which Alan Turing comes up with. Now, what he does, he cleverly replaces A with a computer, with an algorithm. Right? Can we come up with an algorithm, a program that can do the job as well as a human can? And that, he says, is the test of true intelligence. And like as you would suspect, this goes into a lot of natural language processing. How would A, B, and C communicate? Via natural language. And he says that the ultimate test is when a machine can replace a human in a conversation and be able to fool a human thinking that it's actually a human. Like it's indistinguishability is just the true test of intelligence, is what Alan Turing says. So 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 basically, what we take out of here is Alan Turing uses natural language conversations as an unambiguous definition for a concept which is very slippery, like defining something like artificial intelligence, or can machines think with, are they able to do natural language conversations? And as like uh, there is a lot of interesting philosophies and theories around this, which you could go back and do related readings. I discussed the Turing test. There is a very nice movie called Imitation Game. uh, there is also the book The Enigma. That's one. Second is, there is an American philosopher, John Searle, who put forward a Chinese room argument, which is related to this. But he kind of, in theory, argues whether if a machine is able to speak Chinese, does it really know Chinese, or does it have a lot of just statistical guesses to uh, uh, to to speak Chinese or translate into Chinese? And finally, a very interesting argument that like you can search for on the internet is Peter Norvig. Peter Norvig is actually at Google and used to be my boss's boss at a point in time, unrelated. But there's a big debate between Peter Norvig, who has written a seminal textbook on artificial intelligence, and Noam Chomsky, who's a celebrated linguist, of like whether statistical methods actually amount to artificial intelligence or not. Are these statistics actually able to think, right? But these are like interesting conversations I like to have, I like to think about. But I guess we need to take a step back and come back to where we started from, our problem that we want to solve on natural language conversations. So, enough philosophizing. Let me go back to the topic. Okay, so utility conversation is like just a concept that it's like uh, that we define, right? Which is like, for our users, what are some conversations questions that can be of value, right? So for my day-to-day work, I help users finding answers to how many centuries does Virat Kohli have in ODIs, right? But and then the user can ask, what about test matches, right? But you will realize that even with Google at the state of the art, Google has a hard time, or state of the art NLP systems have a hard time understanding context. That's if the user asked use a pointer. If a user asks Kohli have, and then follows by what about test matches, right? It kind of, it is in context, right? So context, being aware of the context is kind of a foundation for conversations in NLP, right? And this kind of utility conversation where we want to find answers to questions can also be applied to other domains. It can be entertainment, like who who was the hero in the movie Sholay. It can be dictionary, what is the meaning of the word onomatopoeia, and it can extend to a lot of domains. So that's one kind of utility conversation we'd like to think about. The second type of utility conversations that we like to think about is accomplishing tasks, booking a train ticket, or buying a pair of shoes, right? So, for example, if you go to the mm, railway ticket counter, it's actually a conversation you have with a person to purchase that train ticket. Like, where do you want to go, what date, right? And they give you the ticket. And on paper, you can replace, or in theory, you can replace that person with a computer, with a natural language processing system, and still be able to communicate seamlessly in language, right? And buy that train ticket. Same applies to buying a pair of shoes when you go to a store, right? And we as humans find it much easier to accomplish these tasks when speaking to somebody like in language, rather than like checking like on a website, clicking on various filters, check boxes, and radio buttons. So we said that there are these two types of utility conversations: one to get one to answer questions, and one to accomplish tasks. But how do we think about, like, have we been successful in accomplishing it? Is Turing test really the bar here? Right? We discussed Turing test earlier, and for any of these conversations, is it important for the human to be able to distinguish whether they're talking to a computer or a human? Maybe not. The bar is too high. Like, in the real world, we don't care about whether there is a computer on the other side or a human on the other side. We just want to get our task done in a relatively robust way, right? uh, what could be another mental model? One is the interactive voice response, right? Where, like, you might have seen this within banks and other places. I think even railways has it, where you call a number, they say press zero, or say English to speak in English, press one for Hindi. Then they say press zero to book a ticket, press one for inquiry. So this is not really, this conversation doesn't seem natural, right? It's very forced, it's not robust, and it doesn't allow to kind of go beyond what is defined here. So we can say that the bar for an interactive voice response system is too low. It's not really a conversation. It's very equivalent to selecting checkboxes online on a website. So So actually, what we want to do is find that our model for the utility conversation, the success of it, is somewhere in the middle. Something which is robust, something which can handle complex queries, something, but it doesn't need to be the Turing test. It's okay if the system makes some mistakes. It's not able to understand you, and you can, like, drive the system back to the right place. So in just to the field of NLP is vast, right? Applied NLP applications of it is vast, and for this presentation, we want to focus it. And the way we focus it is by taking a case study of how to build a conversational agent for task oriented shopping, right? So the system should be able to handle, like, diverse categories, right? Like, system to buy shoes, laptops, phones, whatever, right? And at least understand some broad categories, what we call facets. So it can be price, it can be color, it can be size, right? And depending on the category, the these facets might be different. uh, a laptop might have a facet around how much RAM it has, right? Whereas a shoes might have a facet of whether it's like a Nike shoe or a Adidas shoe, right? So the system be able to understand this. Cool. So now what I'm going to do is show a demo of a launched product. Uh, and actually, before this presentation, I tried playing this and we couldn't hear audio. What I will do is remove my headphones and play the audio. Let me know if you can hear it. If you can't, uh, I'll simply speak out what's happening in the video. So I'm not sure if you were able to hear the sound.
No, sound was not there. So I think you
Oh,
please go through it once and explain.
okay. So what this demo is this is launched in the US. This is Google Assistant, and the user is trying to buy shoes using Assistant, right? So initially they log into Assistant. So initially they say, so it's written over here, right? They say, "Hey Google, I want to buy shoes," right? And based on that, so Google shows this options and also says out loud, "Here are some shoes. Tell me what you like, and I'll help you find more options." This is similar to an experience you'll have in a shoe shop. So the user then says, I'm interested in men's shoes." So now the user wants to look at shoes which are under $100. So the user doesn't like Nike, so the search filter is even refined further based on what the user is saying. Now user goes something which is about the shoe. Let's run. I want to look for running shoes. Color.
मी ते चक्क फेकून दिल्या चप्पल.
So this is interesting. Now, kind of, the user is overriding their previous thing that they had said, that actually they want to buy shoes which are under $50. Cool. So this is like an example of an application of NLP, like providing an in-store shopping experience on the device. This is at least at scale one of the state-of-the-art systems, and for the rest of the presentation, I try to focus on how this is built. If you look at it, users can have like can ask multiple things. They can say, show me sneakers, something under $120. So they can say explicit things that I don't want Nike. It can be a negation, right? They can say, oh, I have overpronation, which is like a certain condition in which about legs, and special shoes are needed in that case. And there are certain things about shoes that the user talks about, right? And we as designers of systems can think of two models of solving the problem. The first model is a user driven interaction, which is what we saw, right? Where the user is mostly driving, asking questions, searching for something, refining, and asking about it, right? And the other model can be like a guided mixed initiative, where the system can explicitly ask, okay, would you like this? Or the user can give suggestions that, like, maybe you would want to explore shoes for running, right? And there can be additions to it, like it can get like FAQs, and the system can chit chat with the user just like in a store, telling them fun facts or whatever, right? But for it's like, I think systems of all categories exist. But for today, we're going to take two simplifying assumptions. The first simplifying assumption is we want to focus on user driven interactions only, no mixed initiative. So we're going to focus on this, where user is driving the conversation and we are just fulfilling the user's requirement, right? And second simplifying assumption is separate out conversation management from the fulfillment of the request. Uh, so in this particular case, given a request, what all shoes are available, how do we fetch all that data from our backend, from our databases, get the catalog and answer the query, that part we're going to separate out, right, from the conversation part. So the conversation part means like understanding what the user is saying, maintaining context of what they had said in the past, and based on that, continue the conversation. And that's the conversation manager. And the second part is the fulfillment, where given the latest state of the conversation, look at our database, look at our catalog, and fulfill the request. So we separate these two out. And you'll see that, like, again, given this is an NLP presentation, I'll be focusing on the first part. So for such a system, this is like a 10,000 feet view. Like, let's say on a mobile, user opens Google Assistant and says, I want to buy shoes, right? So the first system that comes in is called user utterance, but it will typically do kind of like look at the waveform of the sound that has come in, transcribe it into text, understand it, right? So basic things, and also figure out other things about the request. Where is the user located? Is the user located in Bangalore, India, or San Francisco, US, and other things, right? So this is the first part. Next part is dialogue understanding. So this is like the core juicy part for this presentation today, where we are trying to make sense of what the user is saying, right? Which then goes into dialogue state. The dialogue state is kind of a state of the conversation the user has had in the system with the past. And you'll see that there are arrows in both these directions. And what this means is dialogue understanding also takes into account what the user had said in the past, which then kind of goes into a fulfillment library. Think of it in a way that uh, the 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 request from the user is then converted into a search request, which can then be sent to the backend, right, which fetches the search response. This is the fulfillment part I had mentioned. And the GUI, the UI, which is shown to the users, is rendered here. So GUI stands for graphical user interface, and VUI stands for voice user interface, which is useful in conversational assistant. So from the previous slide, we typically say this part is responsible for the conversation itself, whereas the other part is for fulfillment. And again, dialogue state here is very important because it kind of along with dialogue state, we need to put together dialogue understanding and user utterance as a part of the NLP stack. This would be the NLP stack, right? So in this presentation, we need to put together dialogue understanding and the foundation that we've done as a part of this work is something we called like having meaningful dialogue states and contextual language understanding. Let's understand this. Dialogue state is kind of a state of all the conversation that has happened until now, right? And the like would be to have an entire transcript of the whole presentation. Just give me a second. Sorry. Sorry about that. So the transcript of this conversation can be like all the questions which user had asked, right? All the refinements they have made, all the search requests that we have made to the backend, all the search requests that we have made to the backend, and all the responses we have gotten, right? And since conversations can be large, it's often not feasible. It's too bulky to store everything. So the trick here that we have found out is to break the dialogue state into two parts: the query state and the conversation state. So the query state is like in this example, the user starts with I want shoes. They say I want Nike shoes. They say I want under $50 shoes, and then say, oh no, you know what? I want Adidas shoes. So conversation state is like the latest state that we have for this query, which is it's not Nike but Adidas shoes, and still it's under $50. And the conversation state is something different, which is the metadata about this conversation. Has this conversation been successful? Right? Did we understand what the user is saying? Do we need to ask the user, hey, we did not understand, could you repeat the question, or whatever? That's the conversation state. So we separate out the queries as a part of dialogue state. We separate out query state and conversation state. And here is like a small, like minimalistic cartoon example of what these could be. So at any point in time, let's say the user has had 3 rounds of conversations with the system. At this point in time, the query state will be that the category of the shopping category is shoes, type is running, brand might be Nike or Adidas, and color is not red. Whereas the conversation state is this is the 3rd round, right? And what the user right now is trying to do is refining the search that they had initially made. So as user asks more questions, the rounds number will increase. What is the system state? We say Q&A is successful, confidence, and there are like hundreds of such parameters that we use to track conversation state. So the second insight that we have from here is factoring out or decoupling query updates from conversation states is uh, useful, right? So today I'm going to limit the like focus only on query updates. So query updates is this part. So so query updates is this part where, like, given the old query where category is shoes, type is running, and so on, and user says something, right? In this case, the user might says actually any brand is okay, but make sure it's under Nike, under $50. So we have the old query, the new statement which user gave, and using these two inputs to create an output of which is the new query, right? And the way we do it is kind of converting the utterance, the sentence here, into into uh, in you can think of this like similar to assembly language statements, right? These are operations basically that we do on the old query, right? And the crux of the problem that we have distilled down to is converting this natural language sentence into operations. So in some sense it could be thought of as a compiler. In a compiler we get code, and the output of the code is assembly language, right? This is a this in a sense is a natural language compiler where input is a natural language sentence and output is a bunch of operations. You can think of them. It could very well be like uh, a SQL, an SQL database query, right? But in this case, we have modeled it as such as these operations, and and this by itself is a fairly challenging problem, because the same things can be said in so many ways. Like, you can use synonyms. Like, they can, somebody can say portable, somebody can say easy to carry, somebody can say it's not heavy. So there are a lot of synonyms and variations of the same things that can be said, and a system needs to be robust enough to understand that. The second challenge that we face is these utterances can get arbitrarily complex, right? So uh, Nike shoes in red, waterproof but not expensive. So this is in some sense composition of the operations that I'd mentioned, and these can get very big. So the cricket example that I gave earlier in the presentation, like how many runs did Virat Kohli score in 2018 against Australia, right? It can become complex. And in a conversation, it's not just complex sentences, but rather complex sentences coming one after the other, right? So we need context to keep track of context across it. So like with query update, here are the three challenges, right? And this is really the core NLU problem of semantic parsing with context. And this, there have been a lot of recent like innovations in this area. You might have heard with GPT-3, with BERT, right? With question answering, understanding, and with semantic parsing. Like I want to underline semantic parsing here, and say that with semantic parsing, we have a schema of like facets, attributes of objects. So there, in a schema, there are objects, right? And these objects have properties to them. They have like shoes can have a brand Nike, shoes can have cost less than 100, right? And and we need to be like robust enough or flexible enough to be able to handle not just shoes but strollers, smartphones, right? And utterances might not explicitly
नहीं स्कीम तो वही रहेगी ना तृप्ति मैडम. अपने जो सेमेस्टर आने वाले हैं उसमें स्कीम में कोई चेंज तो नहीं सब्जेक्ट्स.
I think there is okay. Cool. So here are some example intents, right? That can come in, and this is where like the concept of semantic parsing comes in. Like so when the user says Nikes only, please. In the end, the operation that's happening here is refinement, right? Other examples of refinement. When they say any color is fine, the operation or the assembly language code or API call, SQL query, whatever you want to think of it, is clear. Here it's a nudge, it's a question, right? So these are examples of intents, and like this defines the schema, and the schema for these objects can have what we call grounded facets or annotations, right? With things we understand, that the brand is Nike, the color is blue, right? But then there are these ungrounded spans. Ungrounded is in NLP literature, ungrounded is referred to things that might be related to the schema but do not match an explicit facet, do not match an explicit annotation. uh, and so like really our problem, the problem statement boils down to, given an example, like given an intent, we want to generate an operation from it, right? So the example, like it's similar to, given a sentence, we want to compile it down to assembly language. So this is what we do. And one innovation that we have done here at Google is trying to make this schema of operations domain agnostic, right? These operations remain the same whether you're buying shoes, whether you are buying laptops or mobile phones. But it's not just related to shopping. Whether you want to do travel search, whether you want to watch a movie, these operations remain the same. I think we have a catalog of some 30 odd intents, right, which cover most verticals. So intent number 3 is to come up with a catalog of intents, right, which is basically the operations which are used to update queries, and try to come up with these intents which work across domains. And kind of coming back to our problem, our problem has been boiled down to the fact that we have, like, to our system, the input is the current query, like the query that has to be updated, the old query, and what the user has said, right? And the output is basically one of these 30 intents along with the arguments that fit in these intents. Think of it as like function calls. And 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 kind of in short, this is kind of the network, the model, the architecture we used to do it. I'll have some water and give everyone 10 seconds to stare at this. So this is like a typical deep learning model. It's called a sequence to sequence plus copy model because the input to this model, the input lower down here, is a sequence of, in this case, contains two things: the original query and the new utterance, and the output is again a sequence, in this case an operation to be done, right? And this architecture, and we use something called a copy model because we want to copy certain things from input to output, like Nike should remain the same between input and output and so on. But this is like a very popular architecture these days where the base layer is BERT does the language understanding part. Then it goes into an encoder decoder model, which is trained on certain data to get this output. As with every machine learning, NLP, like every deep learning task, getting tons of data is quite often becomes the real trick, and I'll share how do we get data in this case to train these models. But like, let me take a path, an interlude to talk about BERT. So BERT stands for is a deep bidirectional transformer network, right, for language understanding. So it stands for bidirectional encoder representations from transformers. I didn't remember it either, right? But BERT, I think, came about in 2019 and revolutionized the area of NLP. And it builds on top of certain ideas from earlier, around pre-training. So the story of modern or deep NLP kind of starts from LSTMs to attention models and transformers to finally BERT and GPT-3, which is the state of art these days. And in this case, there are two interesting ideas that BERT builds on top of. So one, pre-train the model in a task agnostic way. So in this case, what we are essentially doing is understanding the language and understanding like English language in this case, and not related to shopping or any other use case. It's just understanding English language in the model. And the second part, the second idea that uh, that that BERT uses is using attention models to kind of get contextual embeddings. I'll talk about that in a minute, right? What it means. But BERT is typically a two-step process. First is pre-training on the language model, and the second, the model is then fine-tuned for task-specific applications. So in this case, right, what we will do is, I find this a very clever trick, is we try to do a self-supervised like model where we do fill in the blanks. What we do is take Wikipedia and books corpus. These are both huge corpuses of data, and what we do is just mask words and turn it into a fill in the blank statement and train the model to predict these masked words. As humans, we can naturally do this, like, and after surviving a storm got behind, right? We can just predict what's going on. Similarly, here, Chennai, the official name until 1998, is the capital of the Indian state of Tamil Nadu, whatever, right? We can just take pieces of text, remove words, place blanks there, and use that to train the model. So this step one is task agnostic, but the model kind of learns the language statistically. That's step one. And step two is fine tune this model, right, with smaller amounts of training data that is specific to this language. In this case, what we will do is fine tune this model for the shopping use case, where we kind of want to teach the model to convert show me Nike once only please to the operation set value brand equals Nike exclusive. So that's step one and step two. And as I mentioned earlier, the trick or like one insight is how do we generate training data, because ML models require tons of data. So one, we got tons of data for the language models from Wikipedia and books, because we just, it was a domain agnostic. For step two, what we do is first we kind of look at logs, Google data logs, right, and see what kind of queries we have. We find that there is a query for Nike shoes. So, okay, we say that Nike shoes, what it really means is set value brand equals Nike is the operation that we want to generate, right? And then we use these generative data augmentation techniques, where looking at this, we say this is basically like a tag and a category, right? Which means set value. And then we can artificially generate, replace Nike with Adidas, right? We can replace Nike with Puma, whatever, right? We can do blue shoes, you can do waterproof shoes. And because we are artificially generating this for all tags and all categories, we can generate millions and millions of training examples like this. And we can use certain data augmentation techniques, which adds words like Nike shoes, please, I want Nike, I like Nike shoes, right? And we have now programmatically generated millions of training data, which is really like a big problem in machine learning, getting the right data. We also augment the training data with human annotations, right, to kind of get the diverse richness of examples. In this case, make sure it's Nike. Do you have any Nike shoes or whatever, right? And the insight four that I want to share is when we have like using NLP tools, right, with the knowledge of schema for data augmentation can be like a really strong, really powerful tool in our toolkit, right, with just a tiny bit of human annotations to add richness. So we don't need to spend time, effort, money on getting human annotations. We can generate this training data, which can be very powerful. Which brings me to the so this is very useful for the grounded spans, right? But what about the ungrounded spans? If I go earlier here, right, there was this ungrounded span, elegant, razzle dazzle. Like, we don't have a catalog which says we know that Nike, we know these facets about things, but we don't know elegant and razzle dazzle. What do we do about ungrounded spans? Right. So let's say a user says that I need one that fits in my backpack, right? Or will it work for river hiking, or some things which are not like catalog attributes of an object, right? What do? We get product reviews, user reviews. So we what we have seen, what works nicely is traditional unstructured data processing techniques, right? What we do is aggregate product descriptions which are written in by humans, reviews, and aggregate to generate object models. Right, BERT, there's a challenge with BERT that it doesn't scale beyond a few words, but we have two papers in review of how to elevate this problem, where we use like traditional text mining techniques of like this is a really key innovation using bag of sentences models, which model itself is well understood, but using that for ungrounded spans, right? And also using attention patterns to kind of identify these ungrounded spans, and these object embeddings can then be used to fulfill queries for for questions like, will it fit in my backpack? So like the last insight is we want to handle these uh, rich embeddings of like ungrounded spans using rich embeddings, and then the fulfillment engine can easily fulfill what we wanted. Yeah, so I'm at the end of my talk. I want to just quickly take a step back and see the big picture. uh, what happened here, right? So here there are some offline tasks we do, right? So first we have uh, an object model, the schema, right? The operations that we use, right? And that is used to create object understanding for the ungrounded spans. For the grounded spans, or rather, where for the parts which we have schema, we augment it with human input, right? To generate the dialogue model, which is what I showed, which was done with BERT, like the sequence to sequence plus copy model, right? And basically, when a user query comes in, it uses this dialogue model to understand the user query, update the state of the conversation, where we are with the conversation, and then it sends a fulfillment request to the backend. It can be a SQL query, it can be anything, right? Which generates the response and comes back to the US, to the UX. And that was all. So last part of the agenda is to thank everyone. So thank you everyone, and special thanks to Dr. Megha Kamble for inviting me and organizing this session. Thank you, and I'm happy to take any questions.
Right. Thank you very much, sir. Uh, Really, the people are, I'm getting some feedback in the chat box that it was a really very interesting session, and it was very well clearly defined with the help of diagrammatic representation. So it was very much easier to understand the term. One question I had in the chat box, and then audience, please, you can have some question, you can interact through chat box. One question is from Mamta Nayak ma'am. Is BERT can be used for any regional language?
Thanks for the question, Doctor. Absolutely. BERT can be used for regional languages, and in fact, some state-of-the-art work is happening around language translation for regional languages. And the beauty of BERT is we do not need to create any new training data, right? So if we have corpuses of uh, existing text corpuses in regional languages, let's say, if I take an example of Marathi, there is Wikipedia in Marathi. There are Marathi books, right? If we have access to that, we can train BERT model just very simply by masking words and training it to guess words, and that will create a state-of-the-art model that can help accomplish these tasks in regional languages as well. And if I understand correctly, pre-trained BERT models are already available in a lot of languages.
Right. There is one more question. How was the training done on the data set that you have mentioned or used?
Right. So in this case, it was like the training was done in two parts. The first part is like within the model we train fine tune this model where we take domain specific examples where the input is like in this case is show me, let me this go away, it's not going okay. So the input is like show me Nike shoes, and the output that we train for is the operation set value brand equals Nike, right? And the data for this is generated using this augment like data generation trick that I mentioned, where we just use categories like Nike shoes, right, and replace Nike with all the brands we have. And let's say there are 100 brands, Nike shoes multiplied by 100 kind of becomes 100 data points instantly and automatically, right? And with by replacing all the categories we have and using augmentation techniques like Nike shoes please, we 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 get millions and millions of data points that can be used to train. And finally, we can also use human annotations up to a certain extent to get these examples. Now, after step one and step two is done, what we get is this model, right? Where we give input this context uh, uh, along with the sentence, and the output will be the operation that we send, like set value brand equals Nike exclusive, right? And yeah, there are a lot of details here. I can share more pointers, and you could reach out to me separately if you'd like. But like doing a simple search for sequence to sequence plus copy model on Google can take you to various articles of exactly this particular architecture. Thanks for the question.
Right. So lastly, I think we can take one more question. If anyone has some query, please put it in the box. There is one query. Can you share some new research directions in text analysis in the regional language Odia?
In the regional language Uriya, I personally am not very familiar with work specifically in Uriya, but I work closely with my colleagues in Google Research in Bangalore, who who work on this, and if you can reach out to me, I can put you in touch with those people.
Right. I think the people have enjoyed a lot in the session. So I will like to end up the session now. I'm very much thankful once again to the resource person of today's day 2 afternoon session, Alhaad Gokhale from Google, for sparing the valuable time as well as a very informative session with all the faculties who are participating from RGPV affiliated institutions of Madhya Pradesh and AICT affiliated institutions all over India. I'm once again thankful to all the participants for patience hearing. Thank you very much.
All right. Thank you. It was a pleasure being here. Bye.